When we learned about the solubility rules, we learned that alkali metals, ammoniums, and nitrates are all soluble. And therefore, every other type of ionic compound is therefore insoluble. However, even though we say that things are insoluble, something like, for example, silver chloride here, silver chloride, even though we say it is insoluble, it does break apart to a very, very small extent and creates an equilibrium system. So this isn't like a weak acid or a weak base or something like that. This is a salt, and remember, a salt just means an ionic compound. So it just means an insoluble salt that's not an alkali metal, an ammonium, or a nitrate. Okay? And so a little bit of this is going to break apart and create Ag plus and Cl minus. And then, of course, at the same time, the Ag plus and the Cl minus are going to react to reform the AgCl, creating an equilibrium system. When we deal with situations like this, the equilibrium constant that we use is called KSP. And KSP stands for solubility product. Okay, now remember that this is a solid, AgCl solid, so when you write the K equation, you just include the products, Ag plus and Cl minus. And just like any other of the ones that we've done with this, for example, if we had MgOH2, that's also insoluble, the KSP for that would be Mg2 plus times OH minus, and that would be squared, because when that breaks apart, you get Mg2 plus 2 OH minuses. Okay, something like Fe2O3 gets even a little bit more interesting because it's Fe, because there's 2 Fe3 pluses and 3 O2 minuses. So then you would have Fe squared and O2 minus cubed would be the KSP expression there. So just like every other equilibrium constant expression, you use the coefficients from the balanced equation and you do not include the reactants because they are in the solid form. Okay, and the equilibrium constant for this is usually very small. So let's compare two different ones. KSP, let's say you have a KSP of 1.2 times 10 to the negative 18th and one of 1.2 times 10 to the negative 24th. Okay, which one is more soluble? The one that's to the negative 18th or the negative 24th? Just like before, the larger the K value, the more it breaks into ions. So which one is more soluble is the one with the larger KSP value. Okay, so in this case, negative 18th is a larger number than to the negative 24th. Okay, sometimes you'll see it in terms of grams per liter. If you do, you obviously just convert those grams to moles and then you're in molarity. Typically, you do see it in moles per liter. Okay, best way to learn this is just doing some examples. So we're going to do a bunch of examples here. Okay, so number one, we're going to calculate the KSP from what's called the molar solubility. Okay, anytime they give you the molar solubility or the solubility of something, that is what we call the X value. And we'll see what that means here in just a second. But think about when we did ice tables and we had X's and, 0.125 minus X and then X and X. If they say the solubility is this, that is the X value. Not 2X, not 3X. That's just X. So in this case, we have Mx in equilibrium with M2 plus and X2 minus. Okay, so in this case, if they say the solubility, the molar solubility is this, that means that that's the concentration of this, and that's the concentration of this. If it were, for example, 2x here, well, then it would have to be x, this would be 4.15 times 10 to the minus 6, and this one would be double that amount. Okay, so remember, the solubility is the x value. If it's 2x or 3x or something like that, then you have to double it or triple it or maybe cut it in half if it's half. Okay, so they want us to calculate the value of KSP. So KSP is going to equal the concentration of M2 plus times the concentration, that 2, remember, isn't actually there, of X2 minus. And because the solubility is 4.15, that means each of these are 4.15 times 10 to the minus 6. So really, it's just 4.15 times 10 to the minus 6, and that is squared. So 4.15 times 10 to the minus 6 squared equals 1.72 times 10 to the negative 11th would be the KSP value. And with KSP, guys, they're usually even smaller than KA values or KB values. Usually KSP values are really, really small. Sometimes you'll even see them in the negative 20s or negative 30s up here. Negative 11 isn't really one of the smaller ones. Okay, example 2, they want us to calculate the KSP again, but now they're giving us the solubility in grams per liter rather than in moles per liter. So the first thing that we're going to have to do is we have to know the chemical formula of calcium sulfate, and they would give that to you on the test. It is CaSO4. So what we need to do is we need to take 0.66 grams per liter of CaSO4 and just convert those grams to moles. So we need to go to the periodic table. Calcium is 40.1 plus sulfur is 32.1 plus 4 oxygens is 136.2 grams per mole. And now we've just converted our grams per liter to moles per liter. So 0.66 divided by that answer equals 0.00485 molar. Again, that is the solubility, that is the X value. So when this breaks apart, you're going to get Ca2 plus and SO4 2 minus. And again, notice there's a 1 for each of those. So the KSP value is just like that previous one. Since it's a 1-to-1 ratio, it's just that both of those values are the same. So 0.00485 squared equals 2.35 times 10 to the negative 5th. Now, comparing calcium sulfate to this unknown M2 plus X2 minus compound, which of those two is more soluble, calcium sulfate or that MX compound? Absolutely, this is supposed to be a 5. Okay, absolutely it is calcium sulfate because the equilibrium constant value is larger in calcium sulfate. It's only to the negative 5th rather than the other compound, which is to the negative 11th. Okay, example 3. Calculate the molar solubility and the solubility in grams per liter from the KSP value. So the KSP value for AgSO4 is 1.41 times 10 to the minus 5th. Calculate the solubility of Ag2SO4. So first of all, so anytime they give you the KSP value, sometimes that we get that question of, I don't know when to use an ICE table. Anytime they give you the KSP value and are asking you for something else, an ICE table is usually really, really helpful. Okay, so here's one where we're going to have 2 Ag pluses, right, because it's Ag2 plus SO4 2 minus. Okay, now in our ICE table here, again, remember this is a solid. Our first one here is a solid, so that one's out. So initially there's none, there's none. This one's going to go up by X. This one is going to go up by 2X, right, because it's a 1-to-2 ratio. So we've got X and 2X. Now, here's where you really got to be careful with that 2, because this 2 in that Ag plus, you're going to see it pop up twice. It pops up here in the 2X, but then think about the KSP expression. The KSP is going to equal the concentration of Ag plus squared times the concentration of SO4 2 minus. Okay, and we know the KSP is 1.41 times 10 to the minus 5th, and that's going to equal, notice our 2x again. We've got 2x and it's squared. So yep, that 2 in this equation right here is really, really important because again, it shows up here and it also shows up here. And then SO4 2 minus is obviously x. So now we've got 2x and that whole quantity is squared. So that's 4x squared times another x is 4x cubed. So we have 1.41 times 10 to the minus 5th equals 4x cubed. Now to solve for x, we're going to divide by 4, and then we're going to take the cube root of all of that. And yeah, you definitely need to know how to do that. Definitely a calculator question. 1.41 times 10 to the minus fifth divided by 4. Now, there's a couple different ways you can take the cube root of something. Just like when you take the square root, you can raise it to the 1/2 power. You can raise this to the 1/3 power. Okay, most calculators have a button on it. My calculator has a button that looks like this. It's got and then it's got an X right here, which means I have to type in the number 3, and then I'm going to hit that button, and then I'm going to put that answer back in there. Okay, and again, check and see if you've got that as well. And that answer is 1.52 times 10 to the minus second, or 0.0152. Either of those answers obviously are the same thing. Okay, and that is the molar solubility. Remember, that's concentration in moles per liter. Okay, and then if we have to convert that to grams per liter, again, I'm not going to do the whole thing, but 1.52 times 10 to the minus second moles per liter. You just need the molar mass of Ag2SO4, which is 107.9 times 2 plus 32.1 plus 64 equals 311.9 grams, and then we're just going to multiply it by 0.0152. And I get a grams per liter of 4.74 grams per liter. So that's one answer. That's my molarity answer. Okay, example 4. Let's see. The KSP value for lead azide is PbN32, 2.5 times 10 to the negative ninth. Calculate the number of grams that's dissolved in 200 milliliters of a saturated solution of PbN32. So again, they give us the KSP value. So this is another one where we just have to think, what can I do with that information? Okay. So first of all, PbN32 is going to break apart into Pb2 plus 2N3 minuses. And again, they're not going to expect you to know that part. Okay, that is what it is. But again, they wouldn't expect you to know that. So again, this is going to be doing a little bit quicker. This is going to be X. This is going to be 2X again. So you're going to have 2.5 times 10 to the negative ninth is going to equal X times 2X. Again, don't forget to square that. Remember to use that 2 from that balanced equation twice. Once to double it, and then another time to square it. Okay, so again, we have 4X cubed. So I'm going to take 2.5 times 10 to the negative ninth divided by 4, and then I'm going to go 3 to the cube root of that answer equals 8.55. So the molar solubility equals 8.55 times 10 to the negative fourth, and that's moles per liter. Okay, now let's read the question though. Okay, calculate the number of grams that's dissolved in 200 milliliters. So that's how many moles dissolve per liter. Okay, and we can say, well, 1 liter equals 1,000 milliliters. That's one conversion we can do. And then we can say, well, how many milliliters do we have? We have 200 milliliters. Okay. And now they also want it in grams instead of moles. So I'm kind of running out of room here. But the next thing I would do here is I just need the molar mass of PbN32. So lead is 207.2. Nitrogen's 14. There's 6 of them, so that's 84. So that's 291.2. So that's going to go 1 mole on the bottom, 291.2. Okay. Let's see. Now, so we've got liters to cancel. Milliliters are going to cancel. And that seems, so we're going to go 8.55 times 10 to the minus fourth divided by 1,000 times 200 times, let's see, what was that one? 241.2. I can't even read my own handwriting there. I think that's 241.2. If it is, I get an answer of 0.041 grams would be my answer there. Okay, couple more here. And I know this video is long. The more examples you see, the easier this is going to be. Okay, a lot of times using KSP, you're going to have to determine, is a precipitate going to form or not? And you know a precipitate's going to form or not, again, based on Q versus K. So in this problem, we have BaCl2 and K2SO4. And will a precipitate form or not is, you've got barium and you've got sulfate. Clearly, potassium and chlorine, potassium is not going to form a precipitate no matter what because it's an alkali metal. Okay? And so that couldn't be the precipitate. And they even tell you the KSP for barium sulfate is 1.1 times 10 to the minus 10th. So really what we're trying to do here is we're trying to get the concentration of Ba2+, we're trying to get the concentration of SO4 2-, and then we're going to combine those together to determine, and that's going to be our Q value. And then we can compare that with the equilibrium constant to determine our concentration. So if we have 0.00395 molar barium chloride, that means we have 0.00395 moles of barium for every 1 liter. Okay, notice we have 150 milliliters and 550 milliliters. We're combining those together. Okay, so the first thing I'm going to do for barium, I'm going to take 0.00395 moles per liter, and I'm going to multiply by the 0.150 liters. And what that's going to do is that's going to tell me how many moles I have of barium. Okay, so 0.00395 times 0.150 equals 5.9 times 10 to the minus 4th. Okay, and that's moles. Okay, and now I'm going to divide it by the new volume. The new volume is 150 plus 550. That's 700 milliliters, so 0.7 liters. So divided by 0.7 means my new concentration of barium is 8.46 times 10 to the minus 4th. And that's my barium concentration. Okay, now I have to do the same thing with the sulfate. And again, I'm not going to write the whole thing out, but I'll just tell you what I'm doing. I'm taking 0.00775. I'm multiplying by 0.550. And I'm getting 4.2625 times 10 to the minus 3 moles of sulfate. Okay, and now I'm going to take that, and just like here, I'm going to divide by 0.700. And I get 6.09 times 10 to the minus 3rd is equal to the concentration of SO4 2-. Okay, now when I multiply those two together, that's going to give me a Q value. Okay, so I'm going to take that answer, I'm going to multiply it by 8.46 times 10 to the minus 4th, and I get a Q value of 5.15 times 10 to the minus 6th. And notice the equilibrium constant is to the negative 10th. So therefore, Q is greater than K. And then think about the equation. It's barium sulfate solid in equilibrium with Ba2+ and SO4 2-. If Q is greater than K, what does that tell you? Notice the mouth is open to the left, so that means the reaction is going to proceed to the left. Will a precipitate form? Absolutely yes. You are going to get some solid barium sulfate that will form. Okay, here's a couple more. These are from pretty recent AP exams. So these are probably your best examples of recent exams of what type of questions do they ask about KSP. So example 6 and 7, these are the last two. And again, I'm sorry this video is so long. If you need to, just pause and walk away for a little bit, then come back. A student takes a sample of XF2, the fluoride salt of metal X, and mixes it with 100 milliliters of distilled water to form a saturated solution. The value of KSP is 298. Write the balanced chemical equation for the change that occurs when solid XF2 dissolves in water. Okay? And again, if they're giving you a KSP value, you know that's going to be something that is insoluble. So it's going to be XF2, and again, you don't have to put the solid in there, but okay, is in equilibrium with X if fluorine's -1 and there's 2 of them, that means X has to be 2 plus and then 2 F minuses as your products there. Okay? And certainly those would both be aqueous. Again, you didn't have to put that there to get the credit. Okay, and then part B says calculate the concentration of fluoride ions in the saturated solution. So this is very similar to one of our earlier problems where this is going to be X, this is going to be 2X, and we know our KSP expression is going to be X times 2X, and that's going to be squared. Okay, so the KSP value is 4.0 times 10 to the negative 9th, and that again is going to equal X times 2X squared. So once again, we have our 4X cubed. So I'm going to take 4 times 10 to the negative 9th divided by 4. And this has come up. This is like the third time this 4X cubed has come up. That's not that common. Don't think, oh, well, every time it's just going to be 4X cubed. That's not necessarily true. Okay? So divide by 4. And then I'm going to go 3, the cube root. Oops, wrong button, not the square root. 3 cube root of that answer equals, so X equals 1.0 times 10 to the minus 3. Be careful though, that's the X value. That's the concentration of this one. Remember that one's X. Fluoride is 2X. So the concentration, so the fluoride ion concentration is going to equal, so X2 plus is that one, and the fluoride ion is going to equal double that amount, 2.0 times 10 to the minus 3. And then part C, will the solubility of XF2 increase, decrease, or remain the same if it dissolved in 0.10 molar NaF instead of distilled water? So now this is a situation where we're going to add some F minus. So instead of, notice that it says NaF instead of distilled water, which means that right here, this instead of X and 2X, this one would start at 0, and this one would start at, again, that 0.10. So we would have 0.10 here, and then again, X, 2X, so this would be 0.10 plus 2X. Okay, a real easy way to think about this one is what happens when you add some product to your equilibrium system. If I add some F minus, what does the reaction do? Think about it in terms of Le Chatelier's principle. The reaction is going to shift back to the left to use up that. So will the solubility of XF2 increase, decrease, or remain the same? It is going to decrease. Okay, and again, you would use a Le Chatelier's principle explanation there. You can do the math explanation like I was starting to do there, but again, it's much, much easier to say, well, if you add some product, the reaction is going to shift to the left. Okay, so based on Le Chatelier's principle, there will be a shift to the left, and of course, that decreases the solubility. Okay, the more of it that breaks apart, the more soluble it is. The less of it that breaks apart, the less soluble it is. Okay, last one. A student mixes a sample of AgCl with cold distilled water to make a saturated solution. The student finds the following equation for the dissolution of AgCl in water and a KSP value. So there's our equation, there's our KSP value. What's the concentration of Ag plus in the student's solution? So again, KSP is going to equal the concentration of Ag plus times the concentration of Cl minus. And for every one of these, you get one of these. So these two concentrations are equal to each other. So we can go 1.0 times 10 to the minus 10th is going to equal x squared. And then we literally just have to take the square root, 1 times 10 to the negative 10th. And then we're going to take the square root of that. And we get x, which is equal to the concentration of Ag plus as 1.0 times 10 to the minus 5th. Okay, super duper easy. Okay, part B, the value of KSP of another silver salt, AgI, is 8.3 times 10 to the negative 17th. So way, way, way less soluble than AgCl is. If separate saturated solutions of AgI and AgCl are prepared, which solution will have the greater concentration of Ag plus? Justify your answer. Okay, So if they're separate, they're saturated. Saturated means the maximum amount is dissolved and dissociated in the solution. Which solution will have the greater concentration of Ag+? Okay, and hopefully you would see that as AgCl, okay, because it has the larger KSP value, means it is more soluble, producing more Ag+ ions. Okay? Now, that's a lot of examples of KSP. There's, again, a wide variety of different things they can ask. These last couple weren't too bad. Okay, some of the more challenging ones are the ones dealing with, like, will a precipitate form or not. Those are certainly more challenging because you do have to find the Q value. Okay, don't be distracted if they talk about the grams per liter rather than the moles per liter.